Now, we can modify the Drude model to consider free electrons of metal. For metal, there is no drag force, and therefore, it is not necessary to consider relaxation time of the electrons. Therefore, we can start with a simplified form of the equation of motion of electrons under the electric field E. Now, we can consider the dipole moment of electrons P, and inserting the dipole moment with an aid of the harmonic time dependence. We can obtain the relationship between the dipole moment and the electric field. From this, it is possible to express the dielectric constant epsilon sub r as a function of the angular frequency. In this relationship, it should be noted that basic parameter can be defined. This is the plasma frequency, which is a function of electric charge, vacuum permittivity, and mass of the electron and the number density of the electrons. The final factor depends on the materials. Therefore, the plasma frequency is unique parameter for given metals. For typical metal, energy scale at the plasma frequency is about 10 electron volt, which corresponds 124 nanometers in wavelength or 2.4 GHz in frequency. Using the dielectric constant as a function of the angular frequency and the default dispersion relation, it is possible to derive an important relation between the angular frequency and the wave vector as. From this relation, it is possible to describe the behavior of the angular frequency as a function of wave vector k as shown in the red curve in this plot. As can be seen in this figure, we can find that the dispersion relation diverges from the default dispersion curve, which is solid line for small wave vector. It should be noted that the light with frequency smaller than the plasma frequency can't propagate, since it requires the wave vector to be imaginary. The imaginary wave vector is connected in the wave function to make the exponential decay, which prevents the propagation of the electromagnetic wave inside the media. Metals are expected to allow for electron density waves. When the electrons can be combined with photons with designated frequency, they behave like pseudoparticles, which are called plasmons. Metals allow for electromagnetic wave propagation above the plasma frequency. At the surface of metal, surface plasmon polariton can occur, and this is the strong coupling of electrons to electromagnetic field. Polariton denotes any coupled oscillation of photons and dipoles in a medium. Surface plasmon polariton is basically high local field intensities. The local field intensity depends on the wavelength as shown in the lower schematic illustrations. It can be applied to several areas such as guiding light below the diffraction limit, near-field optics, nonlinear optics, sensitive optical studies of surfaces and interfaces, biosensors, study film growth. Surface plasmon polariton is basically transverse M wave coupled to a plasmon, wave of charges on a metal/dielectric interface. Therefore, the wave has to have the component of E transverse to the surface, which is TM polarization. As shown in the upper and lower right images, metallic nanoparticles, or nanostructures such as nanograting can support surface plasmon polariton, and they provide particular resonance peak in the visible spectrum, which makes different colors. Interestingly, metal nanoparticles have specific localized surface plasmonic resonance properties. The LSPR peak width, position, and intensity are the function of size, shape, dielectric constant of the particles and the host media, and polarization. For example, we can observe in this picture that gold-silver alloy nanoparticles appear yellow, orange and red colors if the particle is spherical shape. These spherical metal nanoparticles make strong resonance with relatively shorter wavelength light such as blue or green, and therefore, the colloidal solution appears yellowish or orange-like color. The color is also varied with increasing the concentration of the metallic particles. For gold nanorods, interestingly, the resonance occurs relatively longer wavelengths such as yellow color. Yellow color light suffers strong extinction around the particles, and other colors are scattered, and therefore, the colloidal solutions appears bluish. Interestingly, the resonance peak is blue shifted with increasing the aspect ratio. We can solve Maxwell equation for the metal surface and air to calculate the surface plasmon polariton properties. From the solution, it is possible to derive some important relation. First, for the existence of the surface plasmon polariton, metal and upper media such as air or water should have opposite signs to make the wave vector shave opposite directions. Second, at the surface, it is possible to derive the horizontal part of the wave vector k sub x from the dispersion relation as. Let's remember that dielectric constant of metal decreases with decreasing angular frequency omega. For very small frequency, absolute value of epsilon sub m is much greater than that of insulator epsilon sub d. Then, we can obtain a default dispersion relation. At certain frequency, metal and insulator would have exactly the same absolute value of dielectric constant satisfying epsilon sub m is equal to minus epsilon sub d. At this frequency, wave vector diverges because the denominator approaches to zero. This frequency is called a surface plasmon frequency or omega sub sp. If the frequency is greater than omega sub sp, neither propagation nor vibration is allowed. Therefore, omega sub sp is the limit of the frequency for the formation of surface plasmon polariton. As explained in the previous slide, it is basically impossible to induce surface plasmon polariton on the surface of metal by just shedding the light into the surface. This is due mainly to the fact that the dispersion relation of the surface plasmon polariton requires much higher momentum than the momentum of the incident light. Therefore, there is no coupling of surface plasmon polariton modes to far field. No far-field surface plasmon polariton mode means that it is not possible to use far-field light source to excite the surface plasmon polariton. Therefore, some method of adding the momentum should be associated for the formation of surface plasmon polariton. For example, it is possible to add the momentum by using the dielectric prism with different refractive index. This configuration is called as Kretschmann geometry. This method will give enough momentum for the dispersion relation to make the wave vector of the surface plasmon polariton as shown in the middle figure. Another method is to use nanoscale grating. The grating can provide the built-in momentum for the horizontal part of the surface plasmon polariton wave as shown in the right figure. Using surface plasmon polariton, we can build a very sensitive chemical or biological sensor with great detectivity. The principle relies on the variation of the wave vector of the surface plasmon polariton given by the changes in the refractive index of the surface of gold film. As shown in the left figure, we can experimentally observe the formation of surface plasmon polariton by checking the reflection minimum from the prism at certain incident angle. At this angle, the surface plasmon polariton will obtain the momentum. The minimum reflectivity and the exact position of the incident angle for the formation of surface plasmon polariton strongly depends on the thickness of the glass layer and incident light wavelength. When certain chemical or biological molecules are attached to the gold surface, the refractive index would be changed. This change will give rise to the reflection minimum angle at which the surface plasmon polariton obtain the momentum from the external light. For example, as shown in the right figure, the reflection minimum angle without surface molecules will provide relatively smaller minimum angle. However, as the concentration of the attached molecules on the surface increases, there will be notable shift from the default minimum angle to increased angle. And we can calculate the reflectivity at the two minimum angles, which will be translated into the quantitative information on the concentration of the detected molecules. The surface plasmon polariton can be transported along the metallic nanoparticles array. For example, as shown in the left electron microscope image, an array of 50 nanometers diameter gold particles spaced by 75 nanometers can guide electromagnetic energy at optical frequency below the diffraction limit. Therefore, the array enables communication between nanoscale devices due to a fact that the information transport can occur at light speed. In addition, information transport densities can exceed current electronics. The ever-increasing need for faster information processing and transport is undeniable. Electronic components are running out of steam due to issues with RC delay times. As data rates and component packing densities increase, electrical interconnects become progressively limited by RC delay. As shown in the right figure, for the metallic wire with cross-sectional area of A and length L, the RC delay is proportional to the area and inversely proportional to the length square. Therefore, electronics is aspect ratio limited in speed. The bit rate in optical communications is fundamentally limited only by the carrier frequency. For example, Bmax is smaller than 100 tetrabit per second. But light propagation is subjected to diffraction limit. Therefore, photonics is diffraction limited in size. However, surface plasmon wavelengths can reach nanoscale at optical frequencies. In other words, surface plasmon polaritons are X-ray waves with optical frequencies. Therefore, it is advantageous to use plasmonics compared to the photonics. In conclusion, plasmonics will enable an improved synergy between electronic and photonic devices. Plasmonics naturally interfaces with similar size electronic components. Plasmonics naturally interfaces with similar operating speed photonic networks. For the fast clock and small physical size, the plasmonics can be a great candidate which will replace conventional silicon electronics. Here, I would like to share some thoughts on the plasmonics. As described in the previous slide, it is true that the plasmonics would be the great candidate which will replace the conventional silicon electronics for the nanoscale integrated circuit with high-speed clocking. Due to these properties, plasmonics are expected to be applied for the all-optical circuit for future information technology. The all-optical circuit is composed of a variety of modules working with light or photons at speed of light. This circuit does suffer very little loss, and therefore, does not make heat. And the devices are based on photons, and therefore, power consumption is much lower than the electronics. For the all-optical circuit, it is important to develop nanoscale waveguide, beam splitter, beam collector, super prism, compressor, resonator, nonlinear optical devices, and so on. But the problem is that the plasmonic waveguide with little signal loss is hard to fabricate. As described in the plasmon's properties, surface plasmon polariton propagation length is limited and therefore, signal amplifiers should be accompanied. This requirement is not advantageous for the sub-10 nanometer scale chips. And therefore, we need sub-10 nanometer scale plasmonic waveguide for the all-optical circuit.